All right, good morning, everyone, and thank you for joining us this morning. We have a great presentation for you today in which our speaker will review considerations for sample prep and working solutions. Before I introduce our speaker for today, I want to go over a few housekeeping items. If you have a question, please enter it into the Q&A section as part of Teams, so the little button that says Q&A, and all of your questions will be answered directly after the presentation. I'm also happy to announce that the registration for the Inorganic Ventures Yearly ICP Conference is open. This year's conference will be a slight change over previous years, and for 2022, we're offering a virtual-only portion, which will span the course of 5 days, 2 hours a day, and we're also doing a in-person, very hands-on, very in-depth training session at our lab in Christiansburg, Virginia. So if you are interested in learning more information about that conference or registering, the link will be provided in the chat for today's presentation. Without further delay, I'd like to introduce today's speaker. James King is an inorganic chemist with experience in synthesis and purification. His research is focused on the synthesis and characterization of organometallic compounds to be used as molecular magnets. A native of Hampton, Virginia, James received his undergraduate and graduate degrees from North Carolina A&T State University and Virginia Tech, respectively. James is currently the Director of Production at Inorganic Ventures. James, please take it away.
Thanks, Mike, and welcome everyone to the latest installment of our Be Bold webinar series. My name is James King, and today we're going to discuss matrix considerations you should be familiar with when doing sample preparation and ordering or preparing working solutions for your analyses. I'd like to go through some of the general compatibility rules and guidelines that we here at Inorganic Ventures live by when we design our standards. We're going to go ahead and discuss a few special circumstances to watch out for when making your own standards or ordering standards. And then I want to open things up for a question and answer session. So with that, let's get into it. So at a high level, these are some of the items that you should be considering when you're designing methods, when you're designing standards that you're going to use in your methods. First of all, the analytes involved. What matrices do your analytes of interest require for stability? There are some analytes that are compatible in a number of different matrices. There are some that require specific ones and certain amounts of specific ones. Are there any method or requirements or limitations associated with your method where they require to use a particular acid that might not be compatible with one of your analytes of interest? Always consider anything going on with your instrumentation as far as the analytes you're going to be looking at, the matrices you're going to be using. There could be interferences associated. There could be issues with cleanliness or memory effects in the system. And last but not least, and certainly not least, are there any safety concerns or regulations associated with your lab or your facility? Are any particular acids precluded from even entering the building? These are all things to consider when you're setting up your working solutions in your sample preparations. So I'm going to go through the three most popular mineral acids that we use when we're making standards here at Inorganic Ventures. These are the three most widely used on the ICP, particularly for elemental analysis. I'm going to start with nitric acid. We tend to use nitric acid in a majority of our products for standards because the majority of elements are stable in dilute nitric acid matrices. And while some might require a minimum amounts of other acids, the elements you see highlighted here can all go into dilute nitric acid without the help of any other component to keep them stable. Another reason we tend to use more nitric than anything else, ICP-MS users tend to prefer nitric due to spectral cleanliness. You don't have any interferences associated with nitric acid that you have to worry about. You don't have to worry about any kind of washout issues because you typically will never look at nitrate on an ICP. And while there are some elements here that we're going to definitely talk about as we go through the talk today. The one I did want to point out with respect to nitric is osmium. Osmium is an element that you typically want to try to keep away from nitric to the greatest extent possible. Um, Osmium typically exists in solution as a +4 species, but can get oxidized to a +8 osmium tetroxide that not only carries health risks related to your retinas, but can also make reliable measurements extremely difficult due to its volatility in solution, where you may get situations where the osmium is either in a volatile state, but it's still kind of dissolved in your sample, uh, making for very high readings on your ICP instrument, or it can completely volatilize and you won't even see it in solution. So moving on, I'm going to talk briefly about hydrochloric acid. And if you take a look at the periodic table, you can actually see there are more elements that are stable in dilute HCl matrices than there are even in nitric due to some of the precious metals and whatnot. Um, so technically, you've got more elements that can be dissolved and be stabilized in HCl, but it does carry some drawbacks. One of the biggest drawbacks is chloride can cause interference on the mass spec, particularly for arsenic and vanadium. When you start forming uh, oxygen chloride masses that can hit on vanadium, and then the argon chloride masses that can hit on arsenic. Um, and you will start to see some issues with memory effects from HCl containing stock standards or samples. And that can be a stability concern, particularly if you're a high throughput laboratory. And if you're running something like an HCl matrices through your introduction system in your ICP, and then the next one you run has something like silver or thallium in it, you can tend to see some buildup of an insoluble sodium or thallium chloride building up in your system, which can cause a number of different issues. I did want to highlight silver and thallium and lead in particular. I'm going to talk about these when we get to the special cases. But the reason I wanted to highlight them is uh, technically we can stabilize these elements in HCl with no other acid present. But there's some special circumstances that we need to meet in order to make that happen. And I'll talk about those in just a few minutes. So moving on to the last acid of the main three that we see is hydrofluoric acid. And hydrofluoric is one of the more interesting options when it comes to ICP elemental analysis matrices. There are certain elements that you can see highlighted that require at least some amount of HF for long-term stability. Um, and HF is noted because it can be extremely useful in dissolutions and digestions for a number of different sample types. But the first thing that as an ICP user you should be worried about or concerned about is your introduction system compatibility. Uh, Most ICP instruments ship with glass introduction parts, so you need to be concerned with that because HF tends to attack glass, and you can start to leach out various components of the glass, such as sodium, boron, and silicon, and that can mess up the analysis for those particular elements if you're running them. Um, Another concern, and this one has to do directly with the standards and the samples you might be running, is that rare earth elements and group 2A elements, particularly thorium in particular, tend to precipitate out of solution as fluorides when their concentration is not accounted for. But the interesting thing about the hydrofluoric acid and some of the elements on the table, some elements such as aluminum, boron, phosphorus, bismuth, they can actually be used to tie up excess fluoride ions in solution um, to help mitigate some of those stability issues that you'll see with some of those group 2A and rare earth elements. So there's a lot that we can kind of do here, and we're going to explain and talk about some of that in our special cases section. So just as a bit of a mini wrap up for just talking about these different matrix components, uh, one thing you always want to make sure that you're mindful of matrix matching standards and samples. Uh, you want to make sure that you keep it simple when you're buying and making stock solutions. A lot of times we have customers that will contact us and they'll order something in 5% volume to volume nitric acid, and they plan to mix it with something and they already bought it in 2%. It's not a huge deal, but it helps you achieve reliable measurements a little more if you keep those acid concentrations a little more consistent. Um, you also want to make sure that you're always aware of what kind of impact your matrices and your matrix choices will have on your instrumentation. Again, HCl and nitric, not that big of a deal, although HCl you could see some carryover that you may have to account for with rinsing solutions. But HF, you definitely want to make sure that you're accounting for that, whether you're using some sort of a neutralizing agent like triethanolamine, or whether you're replacing your glass system with um, a Teflon system, introduction system. And most importantly, you want to be aware of alternatives that exist for various compositions and any associated consequences. And what I mean by that is if you have a certain method you're running and it's got a suite of elements, uh, the method may recommend that you run it in nitric, or it may recommend that you buy certain standards in one particular acid or matrix, but you might be able to get it in another one that will effectively help you achieve the same result. And I want to take just a quick detour, and we'll get back and we'll get into the special cases in a moment. Um, and we always want to try to preach this. This is kind of a long-standing inorganic ventures uh, uh, kind of way of life that we always tell people when you're looking at buying stock solutions to mix and make your own working solutions, make sure that your stock solutions are designed with long-term stability in mind, because if they're not, you could have issues in the working solutions that you prepare in your lab. It's always better to have multiple stable stock solutions as opposed to one stock solution that has questionable stability. You can always reach out to your CRM provider for info on starting materials and matrix availabilities to that end. So we talked about some of the different matrix considerations for when you're making standards or when you're doing sample preparation. So now we want to talk about some of the special cases, and a lot of these are going to be ones that we at Inorganic Ventures have come across uh, and in turn solved and overcome. They're written into our procedures, so we know not to kind of go those routes anymore. We're going to talk about just some of the common incompatibilities that we've come across. So in this table, I have a few examples. I mentioned alkaline earth and rare earth fluoride instability. Uh, our common solution to that, and in addition to just simply splitting solutions if the concentrations are too high, once you get about 100 ppm and above, you want to start thinking about splitting the solutions. But below that, 100 to uh, really down to 10 or 1 ppm, as long as you add the alkaline earth and rare earth elements last after you partially dilute the solution, after you've added your acid, your water, and all the other different elements, you tend to be able to mitigate the instability caused by those fluorides coming out of solution. Um, we've done that. We've got stability data on a number of these. So if you have any questions about how specifically or any kind of tips to do that, just let us know and we can put you in the right direction. Um, I mentioned silver and thallium insolubility with chlorides. Um, we go about solving that in two different ways. For silver instability, we can typically put silver in chloride, but we have to bump the concentration up. Typically, we would go with about 10% volume to volume HCl in most solutions that need HCl. For silver, you're going to have to go upwards of maybe 20 or 30, and you're also going to have to protect your solution from light, meaning you have to just keep it covered up and away from light sources. And this generally works. We've got stability data on that as well. A different path for the thallium. Uh, Most CRM providers are going to make thallium solutions from thallium metal, resulting in a thallium plus one species in solution, and that's the species that will become insoluble when exposed to chloride. Um, but it might be worth asking your CRM provider if they have access to thallium oxide starting material and subsequent solutions made from that. Because as the thallium 3 plus, now it can be exposed to chloride and it's perfectly happy in a chloride solution because of the different oxidation state. Just some other ones. I mentioned the osmium volatility due to nitric bearing analytes. So if you expose osmium to too much nitric, you can get that volatility. One way to solve this, we do this with certain solutions, is we simply add osmium after we dilute out the nitric as much as possible that might be carried over from other concentrates of other elements that we have in the solution. Um, Also, arsenic, bismuth, and lead, we have seen some issues of instability when we get to concentrations above 1,000 ppm. Again, these are stock solutions that analysts would use to dilute down. And our solution for that was to simply crank up the amount of nitric that's in solution. We generally crank it up to about 15% volume to volume nitric, when we typically would run somewhere between 2 and 5 in solutions like that. So those are just a few of the general cases we've come across. There were a couple of specific ones I wanted to go over, just because of the nature of them, and and the reason is we want you to start thinking this way when you're either putting together working solutions, when you're designing methods and whatnot. So one of my favorite special cases is trying to combine antimony and mercury. Um, and I'll just go through quickly when it comes to kind of matrix compatibility. Antimony is stable in either hydrofluoric acid, or it can also be stabilized with tartaric acid, just in conjunction with something like nitric or HCl. So you could do HF and nitric, HF and HCl, or tartrate with nitric. And then we actually have stock solutions for both of those in nitric. Um, Mercury, on the other hand, is actually stable in just nitric or in HCl, but the container matters. If you're going to put mercury in nitric only, you need to look into storing it in borosilicate glass, because when mercury is in nitric, it tends to stick to plastic. So your LDPEs, Teflons, things of that nature, you're going to have issues. And now it doesn't matter as the concentration goes up, it tends to matter less, just because the amount that gets stuck to the side is generally around 1 ppm. And once you get up to about 200, 300 ppm and above, that 1 ppm that's sticking to the plastic is basically almost going to be covered in your uncertainty, which is usually around 0.5%. Um, and as stated here, mercury can live in HCl in any container. It's perfectly fine in that acid. Just a couple of other notes associated. Uh, and this would it starts to you start to kind of go down the route of eliminating options for what can keep antimony and mercury stable. We know that tartaric acid reduces mercury to the metallic form. That is not something you want. In addition to uh, the inherent health hazard of having metallic mercury and its volatility, you're also going to have issues measuring on the ICP, because your counts are going to go through the roof. Another point, nitric in concentrations above about 3% volume to volume will begin to degrade tartaric acid, which in turn will destabilize antimony. Again, not good for when you're trying to achieve reliable measurements. And if that wasn't enough, HF, as I mentioned before, attacks borosilicate glass. You start to leach out sodium, boron, silicon, things of that nature, and you risk contamination from those. So what's the solution? When you go through and you kind of do a process of elimination, you're essentially left with a dilute HCl HF as the best available option for long-term stability. Um, Again, somewhat narrow and specific of an example, but these are the type of things that at Inorganic Ventures, our technical support staff, they go through every day when they're quoting solutions and quoting standards that people are going to use for their analyses, and we want to make sure we give you the best option for long-term stability. My last example that I have, and I'm going to go a bit of a different route for this. If anybody is associated with the USP or ICH Q3D testing, you'll recognize these as the 24 elemental impurities associated with that compendium. And uh, when certified reference material providers, Inorganic Ventures is in this boat as well. When they tend to sell these solutions or solutions of these elements, they typically concentrate them or have them concentrated, more concentrated than you would need them for your analyses, and then they break them down into three different solutions. And I've basically kind of color coded these and named them just in general as stock A, stock B, and stock C. Um, and you can see that stock A is stored in dilute HCl. That's due to mercury being present. Um, Stock C is dilute nitric with HF due to the presence of molybdenum, tin, and antimony. And the rest of those guys are fine in nitric. My problem that I see with this is the middle solution. You've got silver, which is classified as 2B in their nomenclature, is being added to the solution with a number of different elements that are typically happy in HCl, and everything is happy in HCl. I mentioned if you want silver in HCl, you have to crank up the HCl and you have to cover it from light because it's light sensitive. Um, this isn't as much of a stability issue as it is an ease of use issue. You can imagine the solution or my recommendation for something like this, if you ever have the opportunity and you're ordering custom standards for example, just simply move silver over into the group 3 elements. Now that takes your stock B matrix from a high HCl and light sensitive solution to just a dilute HCl that can stand on the bench and be fine in any kind of lighter or environment. And the silver is just fine in the dilute nitric and HF solution. So again, ease of use and things of that matter as well to the end user. And we want to try to be cognizant of that whenever possible. So just to summarize and kind of close this up and get ready for some question and answer. A few things to take away: just be familiar with the matrix options for any of your analytes of interest. Um, Another point, uh, when you're putting together your method and you're designing things, uh, start with a method for reliable measurements first, and then strive for better efficiency, not the other way around. Meaning you don't want to go for the quickest one possible, but then compromise your ability to achieve those reliable measurements. Um, and the last step, always be aware of what's in your stock standards, just so you'll know when you're mixing them. You can often troubleshoot a lot of your problems if you know actually what's in them and you have a good understanding of what's soluble or what's compatible with what components beforehand. And then you can always contact your CRM provider uh, to help you out on this end. Thank you for your time. Um, Technical support is available for free for everyone at inorganicventures.com. So take a look if you get a chance and let us know if you have any questions. And at this point, I'll thank you for your time and I will take any questions you might have. Thank you.
Awesome. Well, thank you, James. I had a couple questions start to come in. So we'll go ahead and start going through them. And if anyone else has any questions, please feel free to submit them through the Q&A button down below. And the first question I have is, are there any special considerations for prepping standards containing bromide and iodide for ICP mass spec work?
Um, so that's a good question for mass spec for bromide and iodide. Generally, you want to keep those guys basic. Um, Ammonia is a good matrix for that, but you basically just want to make sure that they're not acidic, because I know the iodide will have issues, um, and bromide will have them as well. So you want to make sure that you use ammonia. You can use Tita, things like that, just to make sure you keep it on the basic side. Um, yeah.
So great. Okay. Second question I have is, what would you suggest to help with washout when running samples containing hydrofluoric acid, but they're looking to they have washout considerations for boron and silicon, and they are using a plastic intro system?
So for boron and silicon, a couple of options. You could also use ammonia, like in the case before, to try to help wash those out of your system. You could also try to use RBS. I think it's a solution. I can't remember where we get it from, but it's I think Mike, you might be able to give us some information. We can if anybody has any questions about it, they can email us at marketing@inorganicventures.com afterwards, and we can send you that info. But I think we get an RBS solution that we dilute down, and we can use that for washout as well. It works pretty good.
Yeah, that does work really well. And in fact, there's a presentation on washouts solutions that's available at inorganicventures.com, our website. If you go under the technical resources, it's a webinar from earlier this year if anyone is interested. It'll also have some good information. So another question's come in, and it already got answered in the chat. So yes, this webinar will be uploaded. So if anyone has a question on that. Next question is, lithium is a problem when in the standard preparation, there's 30 elements in the standard. So could you think of any issue why lithium would be a problem in any standards, James?
We'd probably need some more information on what else is in the solution. I'm not sure if I've ever seen any issues with lithium as far as any kind of compatibility or stability. I'm trying to think, but if you have more information on that, make sure you send it over to us and we can dig a little further. But lithium is generally kind of it's pretty happy in a number of different matrices, even in HF. I've never really seen issues with lithium, so.
Yeah, lithium is usually generally well behaved. So yeah, if you have any more information, please feel free to submit it here, or like James said, you can email marketing@inorganicventures.com and they will make sure it gets to the right person so you get a response. All right, next question. We are using nitric matrix for our ICP OES, and we chronically have low silver LFM results, but not LFB. If we were to add chloride to troubleshoot, would we need to change our rinse as well, currently 5% nitric, or just our calibration and QC stock standards?
So they're looking at silver and they need to add, you said, sorry, say that again, Mike. You said they're trying to add HCl in there?
So they constantly see low silver in a nitric matrix. So if they add chloride to troubleshoot, would they need to change their rinse solution as well?
So that's a good question. I think you may want to change your rinse to maybe add some HCl in there to try to get the yeah, you're going to want to crank up the HCl and make sure that when you're sending it through, it rinses out any potential solid that may form. But I mean, as long as you keep it high and you keep it covered from light, especially when it's in the tube. I know we used to have a method where we actually covered our tubes, our sample tubes here, where when we ran silver and HCl matrices. One thing you may want to adjust is your rinse time. That might help out some. And you may want to monitor for chloride to make sure that you get all that out. But you could probably stick with you might be able to stick with a nitric matrix to rinse out. But you just want to make sure that you take care of the silver beforehand and make sure it's not compromised before you get to that point.
Sounds good. All right. We're going to jump around a little bit. Can you please comment about water purity, trace metal grade, nitric, and HCl? So I think basically what are the main contaminants and you have to worry about with water and nitric and HCl acid?
So for water purity, here we've got a water system that generates us 18 mega ohm DI water. And really the main things you have to worry about as far as water are the just kind of the main contaminants like your sodiums, calcium, things of that nature. As far as trace metal grade nitric and HCl, it's more of the same. I know in HCl, I seem to remember lead being in it, if I'm not mistaken. I think that we found lead in our trace metal grade HCl. And I'm not remembering what our trace metals grade nitric had in it, but it's usually fairly clean, whether we buy it or we were making it in-house.
Yeah, the acids are usually pretty clean. You also want to check your containers that you're, pouring out of. So if you have squirt bottles of dilute nitric or HCl, or you're, squirt bottles of water you're diluting with, sometimes that can create contamination you may not be aware of.
Sure. Good. It's a good question.
All right. Next one, what is your go-to internal standard for ICP OES? Looking for something with the least amount of interferences. Also, what concentration internal standard is the best?
So, not to take the coward's way out, but I'm actually going to throw that one to you, Mike, since you run the ICP MS or the OES and the instruments a lot more often than I do these days. What do you think would be a good one for your OES?
It really depends on what you're looking for. So there are a few different internal standards that we could recommend. It really depends on what you're looking for, because obviously, you know, you want to make sure that what you actually are looking for doesn't have any interference from the the internal standard. So if you could shoot us an email, or if you have the time to sort of add, I'm not sure how long your method is or what you're looking for, we should be able to find a good internal standard. There are options out there. Usually some of the precious metals can be a good one if you're really having trouble, unless of course you're looking for precious metals in your analysis. Also, indium can be a good one. Usually that's probably the most common one that we'll use for OES, just because we look for a lot of different things, and indium is really only prevalent on, one or two OES lines. And again, I think we run at a pretty high concentration just because it's not super, yeah, I'm pretty sure I'm thinking of the right one, indium. The peak on it is not super intense. So yeah, if you have any more information, please feel free to email us, and I'm sure we can find you a good internal standard for your specific application. Really just depends on what you're looking for.
Fair enough.
Cool. All right. The last question that we have right now is, if I use a 5% aqua regia matrix for my samples, do I need to change the matrix from nitric only for my standards?
From my perspective, I'd highly recommend it. Just make sure that that all the analytes that you're using in your standard solutions will be compatible. Adding that HCl in there. Yeah, I'd always recommend trying to matrix match your standards to whatever your sample is going to be in as close as you can.
Very good. All right. That brings us to the end of the question and answer session. But again, just one more time before we close out for the morning, if you have any questions that you would like for us to answer, or any follow-ups, please feel free to shoot an email to marketing@inorganicventures.com, and they will make sure it gets to either James or I or one of our other chemists that would be more than happy to help. I think that's it for us. So I really appreciate your time, and thank you so much for joining us this morning.
Thanks, Mike.
Bye, everyone.